April 9th, 1940, 4:21 in the morning. Drøbak Sound, Oslofjord. The fate of the Norwegian government hangs on a single technical decision made by one man in a cold stone fortress. Colonel Berger Eriksson stands in the command center of Oscarsborg Fortress. Through the darkness and heavy mist, a massive silhouette moves up the channel. It is the German heavy cruiser Blucher. It is the lead ship of the force pushing up the fjord. A brand new heavy cruiser displacing nearly 18,000 tons, carrying troops meant to help seize the capital city of Oslo. The colonel has received no clear orders from his high command. The situation is ambiguous. If he fires and the ship turns out to be a British ally, he will trigger a diplomatic catastrophe. If he hesitates and the ship is a German invader, he will lose his country before sunrise. He looks at the rangefinders. The target is at roughly 1,000 meters. In the world of naval artillery, this is point-blank range. The geometry of the Narrows forces the enemy ship to pass directly in front of his guns. Eriksson makes the choice that defines the campaign. He issues the command to fire. Later accounts say he accepted that he would either be decorated or court-martialed. This is the irreversible step. The primary weapons of the fortress are not modern. They are 3 heavy Krupp guns installed at Oscarsborg in the 1890s. The crews have named the 2 best-known pieces Moses and Aaron. But on this morning, only those 2 can be brought fully into action, while a 3rd gun remains effectively out of the fight. These are 11-inch cannons. They are slow to load and slow to turn. Against a maneuvering target in open ocean at 10 miles, they would be slow to train, slow to correct, and brutally hard to score hits with. But the Blucher is not 10 miles away. It is trapped in a narrow geographic funnel. This scenario is governed by the mechanics of coastal defense ballistics. In ship-to-ship combat, a gunnery officer must calculate wind, swell, target speed, and complex lead times while his own platform is pitching and rolling. A coastal fortress is a fixed platform with zero instability. The firing solutions for every stretch of the channel are pre-calculated and written down in tables. The gunners do not need to guess. They know exactly where the ship is relative to the barrel. The physics are reduced to a simple execution of a trap. The target is forced by the geography into a kill box where the odds of a hit jump dramatically. The heavy cruiser is designed to deflect shells firing from long range which strike the deck at a steep angle. It is not designed to take 11-inch shells fired flat into its superstructure at less than 2,000 yards. The first shell from the gun named Moses slams into the Blucher's upper works near the bridge, ripping through vital functions and throwing the ship into confusion. A second heavy hit follows farther along the ship, feeding fires that begin to race through the center of the cruiser. The ironies of this engagement are physical and industrial. A modern German cruiser is being punished by German guns sold to Norway decades earlier, not because physics breaks the armor scheme, but because close-range hits tear into vulnerable upper works, ignite fires, and cascade damage faster than the crew can contain it. The guns wound the ship, but they do not sink it immediately. The cruiser is burning but still moving. It pushes past the fortress, believing it has survived the ambush. It enters the sector of the concealed torpedo battery on Nordre Kaholmen. This is not a deck launcher the cruiser can spot and bracket. It is a shore installation built into rock, meant to throw straight-running torpedoes across the Narrows from the same merciless range. No modern homing, just a hard, hidden shot timed by men who know the channel. The torpedoes are launched from the underwater tubes. They run true. The first strike drives into the forward part of the ship. The second tears into the machinery spaces that keep the cruiser alive. The cumulative damage is catastrophic. The 11-inch shells strip the command and control. The fire weakened the structure. The torpedoes open the hull to the sea. The ship loses all power. The pumps fail. The heavy cruiser begins to list. Around 6:22, it rolls, capsizes, and sinks, taking hundreds of sailors and the heavy equipment for the invasion down with it. The wreck comes to rest with its keel up in the Drøbak Narrows at roughly 80 to 90 meters of depth, depending on where you measure along the hull. The hull is inverted, and parts of the ship's upper works and fittings sit close to the bottom, battered by the sinking and the slope. But the wreck remains a coherent mass of steel, not a flattened scrap heap. The ship is dead, but it is not gone. Inside the steel carcass, significant quantities of heavy fuel oil can remain trapped in tanks and voids. As decades pass, salt water attacks seams, fasteners, and plating, and the wreck shifts from war grave to pollution concern. The question changes from how the ship was lost to how much residue can escape, and how to reduce that risk without desecrating a grave. The defining characteristic of the wreck site is not the number on the depth gauge, but the way the hull sits. The heavy cruiser lies inverted on the fjord floor, upperworks mashed into silt, and slope-scoured debris, yet the silhouette still reads as a single mass of steel. The keel points up toward the surface, and the ship becomes a capsized fortress. Floor turned to ceiling, the architect's load paths flipped the wrong way. And it sits that way on a slope. The wreck rests on a slope in the same deep band of the Narrows. Down here, hydrostatic pressure rules the logistics. Close to 9 atmospheres of absolute pressure, cold temperatures, and low visibility turn every intervention into a high-risk, high-cost operation. The pressure is a hard limiter for humans and equipment. Even if the flooded hull itself is largely pressure balanced with the sea, a diver breathing standard compressed air at depths on the order of 260 to 300 feet would face severe nitrogen narcosis and a sharply rising risk of oxygen toxicity, along with punishing gas density that makes breathing hard work. To operate in this zone, teams typically rely on mixed gas methods and tightly controlled procedures, sometimes including saturation protocols when the job demands long exposure. At this depth, useful bottom time is rationed. A job that takes an hour on the surface can demand long decompression and meticulous planning down here, turning simple tasks into logistical marathons. Every movement is expensive, slow, and dangerous. And once the hull is flooded, the steel itself is mostly pressure balanced with the sea. The slow killers shift to corrosion, currents, silt movement, and the relentless weight of a ship resting upside down on an uneven slope. The armor belt meant to guard the waterline is now buried in mud. The unarmored keel takes the current. Inversion also scrambles the internal map, leaving fuel tanks that once sat low in the hull closer to the highest parts of the wreck's structure. Oil is lighter than water, and even heavy bunker fuel will keep hunting for the highest path it can find. In an inverted hull, high points the wrong way. Seams and plates near the uppermost steel become the places where trapped fuel wants to go. Upright, a breach can flood a tank while oil rises inside it. Upside down, the wrong breach can let oil out first. The wreck is no longer a ship. It is a compromised container with its weak points facing the fjord. The environment of the Drøbak Sound adds a dynamic layer of hostility. The water is cold for much of the year, and in winter it can hover near freezing, slowing some chemical processes while making every minute underwater harsher on people and equipment. The Sound is a tidal choke point. Strong currents scour the site, moving enormous volumes of water past the wreck with every tide cycle. This constant movement stirs up the fine silt on the bottom. Visibility is often reduced to just a few feet. A diver or a remote sensor cannot see the entire ship at once. They can only see the small patch of steel directly in front of their face lamp. This combination of depth, darkness, and inversion creates a specific type of forensic problem. The engineers know the oil was there. They know the hull has been weakening. But they cannot verify the thickness of the steel plates simply by looking at them. Corrosion progresses unevenly, driven by seawater chemistry, oxygen availability, currents, microbial activity, and the way different materials meet and couple across decades. The wreck is a silent container holding a viscous threat, and the only way to reduce that risk is to intervene without shattering a fragile equilibrium. The engineering team in 1994 faces a trade-off that balances precise control against the risk of total structural failure. To remove the threat, they must deliberately breach the hull of the capsized vessel. If they drill into the tanks incorrectly, the weakened steel could tear open, releasing a large fraction of the payload into the Oslofjord in a single black tide. If they do nothing, slow corrosion could eventually guarantee the same outcome. The decision is made to intervene surgically. The contract is awarded to a specialist subsea intervention team. The enemy in this phase is not just the depth or the pressure, but the physical state of the cargo itself. The fuel inside the Blucher is heavy bunker oil. In the warm engine room of a living ship, this substance flows like thick syrup. But after 50 years in near-freezing water, the physics of viscosity have changed the material. It has congealed into a semi-solid mass, similar to cold asphalt or tar. A standard salvage pump cannot move it. If a diver were to open a valve, the oil would simply sit there, refusing to flow. To extract it, the engineers must change its physical state. The solution is a technique often described as hot tapping, a sealed, controlled way to create an access point into a live or sensitive system, without letting its contents escape during the moment of penetration. On the wreck, the goal is the same in spirit: maintain control, contain the risk, and turn a brittle, submerged tank into something that can be safely emptied. Specialized equipment is fixed to the plating, a small opening is made under containment, and a controlled connection is established so the tank can be managed rather than ruptured. Because the ship is inverted, every tank must be approached as a geometry problem, not a routine pump-out. Heat is introduced under containment to change the fuel's viscosity, and the liquefied oil is then drawn off through controlled access points. The physics of buoyancy still matters, but the operation is engineered around sealing, monitoring, and preventing a sudden tear in weakened steel. This is not a single operation, it is a repetitive industrial campaign. The divers and remote systems must perform the surgery across multiple bunkers and storage spaces along the length of the inverted hull. Over the course of the campaign, they make well over 100 taps, 100+ seals to trust, and 100+ chances for brittle steel to crack or a connection to fail. The work is slow and methodical, done blind in that cold water among sharp wreckage. The extraction continues until the monitoring indicates the tanks have been drained as far as the operation can safely take them. The final tally of recovered material is massive. A huge volume of bunker fuel is reported as removed in the 1994 campaign, along with contaminated water and residues handled as waste. This is fuel loaded for the dash up the fjord, finally pulled out of the ecosystem half a century later. The immediate environmental risk is sharply reduced. The oil is shipped away for disposal and the equipment is recovered. But the departure of the salvage barges leaves a new reality on the bottom of the Sound. The wreck bears the scars of that intervention: multiple sealed access points, plugs, and patched penetrations left behind as evidence of a controlled operation. The bulk of the oil pressure is gone, replaced by seawater in spaces that were once filled with fuel. The oil threat is reduced, but the steel remains and the clock is still ticking. For the next 3 decades, the salt water will continue to eat away at fasteners, seams, and plating, hiding the true state of the structural decay until a new generation of technology arrives to see what is happening in the dark. For the next 3 decades after the pump-out, the violence becomes invisible. With the toxic fluid largely reduced, gravity takes over, working on a structure that is slowly dissolving. This is the risk shadow, a calm surface above and a failing warship below, carrying its own weight in silence. The primary antagonist in this structural crisis is the physics of inverted wreck stability. A warship is designed with a specific distribution of weight to survive in an upright position. The heavy armor belt, the massive engines, and the ammunition magazines are placed low in the hull to lower the center of gravity. The structural frames are engineered to support these loads from below, transferring the weight to the buoyant hull. When the ship capsizes and comes to rest upside down, the load path flips. What was supported from below is now hanging in tension. Engines and armored decks end up suspended above the silt, pulling on rivets and beams that were never meant to carry them that way. And the superstructure, bridge and heavy gun turrets included, becomes the foundation taking the crush. The ship is top-heavy, but because it is inverted, that heavy top is now the foundation driving into the seabed. As the internal supports weaken, the risk is not just that the ship will collapse, but that it will break apart in unpredictable ways, shifting thousands of tons of steel in seconds. This mechanical stress is accelerated by a chemical process known as galvanic corrosion. The wreck is not a single piece of metal, it is a complex assembly of different materials. There are steel plates, iron rivets, bronze propellers, and copper wiring. When these dissimilar metals are submerged in an electrolyte like salt water and physically connected, they form a massive electrical battery. Current flows between them. One metal becomes the cathode and is protected, while the other becomes the anode and is sacrificed. In the cold, dark waters of the Drøbak Sound, the steel hull acts as the anode. It gives up its electrons to the sea, causing the metal to physically waste away. The process is slow but relentless. It attacks the welds and the rivets first. A steel plate might look intact to a diver, but the connection points holding it to the frame may be reduced to rust dust. The structural integrity becomes a mirage. The hull plating, which once deflected 11-inch shells, is thinning year by year, turning into a fragile skin that hides the internal collapse. The debris field surrounding the main wreck adds a layer of complexity. The ship carried munitions, and it is prudent to assume that some ordnance or ammunition may still be present in or around the site. That possibility forces strict safety constraints on any survey or intervention. Keep distance where required, minimize disturbance, and treat the seabed as a controlled hazard zone. As the structure degrades, even inert objects can become obstacles, and any movement of debris can complicate future access. The engineers monitoring the site face a critical blind spot. They know the corrosion is happening. They know the gravity is pulling the ship apart. But they cannot see inside the inverted hull to measure the rate of failure. Traditional divers cannot safely enter the unstable, upside-down interior. The old drawings from 1940 are no longer a map of the ship. They are a memory of what it used to be. The reality is a corroding labyrinth in the dark. To understand the true timeline of the collapse, the survey team needs a new way to strip the water away and see the naked steel. They need a technology that can touch the wreck without making physical contact. The primary enemy of underwater observation is turbidity. In the Drøbak Sound, suspended silt and organic matter turn ordinary light into backscatter, a veil of white noise that hides structure. But to judge the Blucher's integrity in 2025, the team needs the whole 600-foot hull in one coherent view. Since the water will not give them that, they need a technology that can digitally drain the ocean. The tool deployed for this mission is the WWII Discovery Stereo Camera System. It rides on a remotely operated vehicle, an ROV, a steady flight platform, the surveyor's equivalent of a fixed gun deck. The sensor does not just record video. It captures dense, overlapping stereo imagery while the robot flies a precise grid over the wreck, maintaining a constant altitude above the corroding steel. It slices through the darkness with controlled strobe lighting that freezes motion and eliminates blur. The intelligence behind this survey is a process called VSLAM, or Visual Simultaneous Localization and Mapping. In a featureless environment like the open ocean, a robot can easily get lost. It does not know if it has drifted left or right. VSLAM solves this by using the wreck itself as a navigation beacon. The computer analyzes imagery in real time. It identifies distinct, high-contrast features on the hull, such as a rivet head, a torn plate, or a patch of marine growth. By tracking how these thousands of feature points move from one frame to the next, the software calculates the position and orientation of the robot relative to the ship. It builds a map of the environment while simultaneously figuring out where it is located within that map. It is a continuous geometric feedback loop. The robot uses the wreckage to find its path, and in doing so, it digitizes the wreckage to within millimeters. The system corrects for distortion and uneven lighting so the geometry stays true. The output of this operation is not a movie. It is a dense point cloud. The computer combines millions of individual laser measurements and pixels to create a three-dimensional model. This is the digital twin. On the computer screens in the control room, the murky green water is stripped away. The darkness is replaced by artificial light. For the first time since 1940, the entire cruiser is visible in a single view. The engineers can rotate the model, zoom in on a specific valve, or measure the deformation of a blast plate to within a fraction of an inch. With the digital twin, the engineers can inspect the wreck without touching it. They can set today's geometry against the original blueprints from the 1930s, trace the hull lines, and measure where gravity is bending steel out of shape, turning the risk shadow into numbers. The scan also becomes a baseline. Future surveys can be overlaid to show the rate of collapse over time. And then the model does what eyewitnesses never could. It reveals the wounds that killed the ship, shell strikes and torpedo damage, preserved as hard geometry on the seabed, a freeze frame that will not corrode. The ghost is now captured in the machine, ready to testify. The final assembly of the digital twin brings the forensic evidence into a single, undeniable frame. For decades, the specific mechanics of the kill were reconstructed from the chaotic testimony of survivors and the logs of the fortress. Now, the point cloud adds hard geometry from the seabed. The scan helps confirm the lethal efficiency of vintage weapons used at close range. The hull plating near the boiler rooms and the turbine section is not just torn, it is blasted inward with a specific signature that matches the detonation of the 45-centimeter Whitehead torpedoes. The damage map revisits a long debate between the fires above the waterline and the breaches below it. The model can show where the hull is torn and where structures have failed, letting investigators test old assumptions against measured geometry. Some recent interpretations suggest that progressive flooding through major hull breaches played a more decisive role in the final loss than the torpedo impacts alone long believed responsible. What remains undeniable is the paradox of the engagement. A modern cruiser, forced into a narrow channel, was disabled and destroyed by weapons that were already old. This visualization also highlights the critical importance of the 1994 intervention. The model can reveal scars and access points consistent with a major oil removal campaign carried out on the inverted hull. If large volumes of bunker fuel were still trapped inside today, the corrosion mapping would read like a forecast of disaster. But because the bulk of the oil was removed in 1994, reported on the order of 1,000 tons, the environmental risk was sharply reduced. The ship is still collapsing. It is simply collapsing under watch, with far less fuel left to spill. The status of the wreck is now governed by the concept of war grave protection. The Blucher contains the remains of hundreds of men who went down with the ship in 1940. In Norway, the site is protected under heritage regulations and managed with strict restrictions. It is treated not as a resource to be salvaged, but as a place to be respected. Unauthorized disturbance and looting are forbidden, and any work on or near the wreck is tightly controlled. Those restrictions leave only one workable path forward: watch without touching. The non-contact survey method used in 2024 breaks the ethical deadlock, letting engineers monitor steel loss and bottom stability while leaving the crew's resting place undisturbed. And the digital twin opens a virtual visit for the public and historians, preserving the narrative without violating the grave. The wreck lies east of Askholmen, resting in the dark, cold current. The artillery shells and the torpedoes did their work in 1940. The salvage divers did their work in 1994, cutting the worst of the pollution risk down. Now, the robots add the next layer, a way to watch the wreck without touching it. The imperative has changed from urgent defense to quiet observation. The story is not closed. It is monitored.